Okay, this is for Integrated 2, Section 3.1.4. Now we're going to talk about unions, intersections, and complements. Kind of alluded at complements yesterday or a couple of days ago when we were trying to find the probability of a tank top, I think is what it was. So an event. So we've got some vocabulary that we need to go through. This can be found directly in your notes as well. So the event, it's a subset of outcomes. So for example, we're going to be using this example a couple of times. We're going to choose an integer from 1 through 10. Okay, the sample space is everything that could happen. So the sample space is 1, 2, 3, 4, 5, so on and so forth through 10. But then we want to talk about specific events. Again, it's a subset of the outcome, so part of it. We could do the event of a prime number. Well, as a reminder, prime numbers are numbers that are divisible only by 1 in themselves, excluding the number 1. 1 is not prime or composite. It's very special. We call it irreducible, which you'll talk about if you ever decide to major in math in college. Then we have our even numbers, which would be 2, 4, 6, 8, 10. So prime is one of the subsets, or it is an event out of the sample space. And then moving down, so we talk about a complement. So for example, just like the tank top question, if we wanted to find the complement of the prime numbers, well, it's everything that isn't in the prime numbered list. So when we say complement of prime numbers, we're basically saying not prime numbers. So that's what our complement is. Okay, and then an intersection is the event when both the first and the second event occur. So a situation, kind of like when we were choosing outfits in our warm-up the other day. So we have our intersection of the events, 2, 3, 5, 7, so those are our primes, and 2, 4, 6, 8, 10, those were our evens. The only thing that belongs in both of them, so intersection belongs in both of them, is 2. There's something very special about the number 2. So we see that 2 is the only number that occurs in both of the lists. So we would say that it is in the intersection of the 2. Okay, moving on, we're still using that example on the previous slide. So again, straight from the notes. Union is when we talk about the first or the second or both. That's actually okay too. But we do have to be a little careful here when we're trying to figure out the union. So first or second or both is the possibility of double counting. That's going to be an issue. So when we get down to formulas here, you're going to see there's a subtraction component to this. And that really is to just get rid of the double count of something that we already did. So we still have our events 2, 3, 5, 7 and our event 2, 4, 6, 8, 10. The union is when you marry them together. I think that's the best way to put it. So take all of the numbers in the first event and all of the numbers in the second event, and we put them together as a single event itself. Probability of randomly choosing a number that is prime or even. So prime or even is going to be at 8 out of 10. Now remember, the 10 comes from the fact that we had the entire sample space of 1 through 10. So our 10 comes from the total sample space. The 8 comes from, well, how many entries do we actually have in here? So if we go through and count everything, we get a 1, 2, 3, 4, 5, 6, 7, 8. So that's where our 8 comes from. Okay. So there's 8 numbers in the union, all right, 10 in the sample space. Probability of the union of 2 events, it can actually use a calculation here, and it's called the addition rule. But you be careful with this because we do have to get rid of that overlap, so the thing that gets counted twice. So the probability of event A or B would be the probability of A plus the probability of B. However, we want to make sure that we subtract one of the overlaps because it's going to end up getting counted double. So we just got to get rid of the extra one. So we also have probability of A union B is probability of A plus probability of B minus probability of A intersect B. All right, if we talk about notation here, so I want to introduce you to it just in case you see it somewhere along the lines. We can say the probability of A. The union sign looks like a capital U without the tail on it. So A union B is probability of A plus the probability of B minus, and then I think you may have actually seen these notations. Probability of A intersect looks like the U turned upside down. So intersect B. So just some notation. You don't necessarily need to know it for me. It doesn't, I don't think, show up in your textbook, but it may show up in future problems if you go through and you practice things. Okay, so then if we take a look at the event, A, which we know was the prime numbers, B was the even numbers, then the probability of A is 4 out of 10 because there are 4 entries in list A. And then we had 10 total in our sample space. Probability of event B, there's 5 numbers total in that list out of 10 numbers in the entire sample space. And then the probability of A and B is going to be 1/10. And that's where that subtraction thing comes in. You can kind of see it down here at the bottom. You'll see that we've got that one number that belongs in both of the lists. So you got to be careful that you only counted it once and not twice. So the addition rule is nice, but don't forget to subtract the overlap, only because it's been counted multiple times. Okay, so here we have an example. So let's go ahead and take a look at this. We have a normal 6-sided die, which means it's got 1 through 6, a different number on each face, and an equally likely chance of landing on any of those. We want to find the probability of a number divisible by 2. All right, so we've got the sample space. So basically everything that could happen. So everything that could happen is 1, 2, 3, 4, 5, and then 6. Okay, we want to find the probability of a number divisible by 2 or 3. So probability of 2 or divisible by 2. So probability divisible by 2 plus probability divisible by 3 minus, just in case there's an overlap, probability of divisible by 2 or 3. Okay. Or divisible by both. I guess I'll put it that way. I don't want to get these extra ors kind of flying around. So probability divisible by both. All right, so if I take a look at the list, I know that there are 6 total entries. All of the numbers divisible by 2. I think I'm going to do some color coding here. So divisible by 2, well, let's see. We've got 2, 4, 6. So that's going to be 3 numbers. Okay, plus we still have 6 items here. Let's color code this one green. So divisible by 3. Well, divisible by 3 is 3 and 6. So that's 2 numbers. Minus, there are still 6 total numbers. Now you want to look for the overlap and look and see if any of them actually counted twice. So if you look, I have the number 6 also has the red underline, counted the first time, and the green bar across the top. Again, just my color coding. So that means that it was counted for red and for green, which means I need to get rid of the fact that I counted it twice. So that's going to give me 1/6. So it's counted once, actually counted twice already. So now go through, do the math. It looks like we're going to get 4 out of 6, which we can simplify to 2/3. Okay, so here we've got this kind of a cumulative example. So we've got some situation that has to do with marbles, then, or a bag of marbles. Then we also have this spinner. I want to come up with all the different probabilities. So at this point, I would highly, highly, highly recommend that you either create an area model because there's only 2 things that are happening here, so 2 variables at work, or create a tree diagram before moving on and solving the problems. Then, since we've been practicing these already, I would pause. If it were me, I'd go through, fill out my model, see if you can answer the questions. So just doing a quick check-in on my model, I decided to go ahead and just use an area model only because it was 2 variables at work. So I chose marbles across the top and I used the information was given to me. I know that there are 20 total marbles because I added up the 5, the 9, and the 6, and then figured out what the ratios were for each color. And then down the side, I decided to use the spinner. Okay, so then now I want to be able to answer my question. So double check your model against mine, whether it be area or tree. You should have the same probabilities down through the branches if you did a tree diagram, and then see if you can answer these questions. Okay, before I go through and show question 4, I do want to take a look at the ones that we have so far. So with question number 1, we're going to find the probability of a green marble and a red spin. So we can go back to the area model, or you can go down to the tree diagram and find where those things overlap each other. Now, since we know that pulling a marble out of the bag and spinning the spinner do not affect each other, I know that I can just extract that portion straight from the table. So if you take a look over at my area model, it's that red box. That's where the 5/80 came out of. So I just went to green marble, spin red. Get 5/80. If you simplify that, that's 1/16. Then we want to find the probability of getting 2 blues. So probability of blue and blue. So we're going to go back to the area model, find where the blue and the blue overlap. It's the blue box that I identified. That's 6/40, so 3/20. Now number three is a complement question. So I want to find the probability of not getting red. So I set it up so that I know the probability of not getting red. Well, if I add probability of red and probability of not red, that's going to have to be 100%. So if I then solve that equation for probability of not red, then it's going to be 1 minus the probability of red. So there's a couple of ways that you could do this. We could go up to the probability of getting a red marble. So red marble, you'll see I circled it up at the top. That's 9/20. All right. Then we could say, okay, what if we got a red spin? Go over, take a look at the spinner side. I circled the red spin. So that's where I got the 9/20 and the 1/4. But you'll notice that by counting that entire column for the 9/20 and the entire row of 1/4, I double counted the intersection, that box where they both come together, which is red. So that's where the 9/80 comes from. That's the red overlap. Because it was counted for both of them, I have to subtract it once so it doesn't get double counted. And then if you add combine all of those things inside the parentheses, that's going to give you 47/80. Then subtract that from 1. So remember, probability of red and probability of not red are going to represent 100%. And then our last question. So probability of red marble or green spin. So we're going to separate them because there is an overlap. Probability of red marble, if you look back in the table, I boxed it in green, is 9/20. Then the probability of spinning green, boxed it in green, that's 1/4. But then because that row and that column overlap each other, we have a double count. And the double count I circled in green, that's the 9/80. So then if I go through and I combine these, get a common denominator, I will get 47/80.